Hello guys, this is Paul McWhorter with TopTechBoy.com, and we are here today with episode number 39 in our incredible new tutorial series where you are unleashing the power of your Raspberry Pi Pico W. What I will need you to do is pour yourself a nice tall glass of ice cold coffee. That would be straight up black coffee poured over ice, no sugar, no sweeteners, none needed. And as you're pouring your coffee, as always, I want to give a shout out to our friends over at Sunfounder. Sunfounder is actually sponsoring this most excellent series of video lessons. And in this class, we will be using the Kepler kit for Raspberry Pi Pico W. Now, most of you guys probably already have your gear, but if you don't, look down in the description. There is a link over to Amazon. You can hop on over there and pick your kit up. And believe me, your life and my life are going to be a whole lot easier if we are working on identical hardware. But enough of this shameless self-promotion. Let's jump in and talk about what I am going to teach you today. I am going to teach you a second lesson on practical trigonometry, where you learn the essentials of trigonometry necessary to solve real-life problems, and you don't just memorize it, but you understand it. I gave the first lesson last week where I sort of showed you how easy it is to do trigonometry. And just to drive those points home, we're going to have one more lesson today, and then we're going to be moving on to Raspberry Pi, more Raspberry Pi Pico W projects. So why am I teaching you trigonometry all of a sudden out of nowhere in the middle of a Raspberry Pi Pico W class? Well, the reason is our next project is going to require you to understand trigonometry. And this is showing you the project. We are using the MPU 6050 out of the Sunfounder kit, and I've made a little tilt-o-matic out of it. So as I tilt it, it acts like a digital level, but it works both in the x-axis and the y-axis, and it gives you an actual quantitative measurement for the tilt angle in those two directions. Well, that's a really cool project, but I don't want you to just come in and copy my code or try to memorize what I did. I want you to understand it so that you can not only do this project, but you can do projects like it in the future. And in order to be able to do that, you've got to understand trigonometry. Now, last week, I'll just kind of recap what we learned last week. What we learned last week is that trigonometry is really not about triangles. It is about circles. And what I taught you to think about is, imagine just having a vector and starting at 0 degrees and then rotating that vector counterclockwise from 0 to 360 degrees. As we do that, the tip of that vector, the tip of that stylus traces out a circle, right? It traces out a circle. And at every point, you have an x value and a y value. So in order to understand a circle, you have to take an angle, and then you have to change that angle between 0 and 360 degrees. And then for every point, you can calculate the x and y value of the coordinate on the circle. And it's very easy to do. The x value is the radius times the cosine of the angle, the radius times the cosine of the angle, and the y value is the radius times the sine of the angle. So as you go around, you can calculate the x and the y for every angle. Okay, how do you calculate cosine and sine? You do that inside of MicroPython or whatever programming language that you are using. Now, we did learn last week that as human beings, we usually think in terms of degrees, where we go 0, 90, 180, 270, 360, 360 degrees in a circle. But most programming languages use a different measure for degrees, and they use radians. And with radians, instead of 360 degrees, you have 2 pi radians. And so if you were going to calculate sines and cosines, you've got to first convert degrees to radians. And we can do that using this equation where you take your degrees, you divide by 360, you multiply by 2 pi, and then you get your measurement in radians. And then that is what you plug into the sines and cosines. We also pointed out where it sometimes, instead of being given an angle and you have to calculate x and y, sometimes you are given an x or maybe an x and a radius, and then you want to calculate the angle. So the angle that you have is the arc cosine, the a cosine of x divided by r, or you could get it similarly by saying it's the arc sine of y divided by r, or you can say that it is the arc tangent of y divided by x. So this is 1, 2, 3 ways to calculate the same angle. 1, 2, 3 ways to calculate the same angle. And so that really is all of trigonometry in a nutshell. All of trigonometry in a nutshell is to think about a circle, think about the xy coordinates along the circumference of the circle, and calculate them based on an angle that you're going between 0 and 360. Okay, now that makes it really, really easy to think about trigonometry, but then sometimes you just have problems that really do just involve a triangle. And therefore, imagine here in my picture if the circle just went away and that triangle just started floating around. All of a sudden, what is x, what is y, what is theta, what is radius? All of those things you lose track of because the circle disappeared. So what we need is a way to label this thing that will work even if the circle disappears, even if the circle goes away. And this is how we are going to do that. This is what we are going to do. We are going to call these different things. Now the radius here, let me see if I can back up a little bit more here. Give me just a second. Okay, the radius here, instead of calling it radius, we are going to call that the hypotenuse, H-Y-P, short for hypotenuse. So anytime you have a right triangle, the hypotenuse is the what? It's the long side, and it is the side opposite of the right angle. Right here is the right angle. Here, the side opposite of the right angle is the hypotenuse. It is the long leg of the triangle, and it's what used to be the radius when we had a circle there. So now we have a hypotenuse. Okay, now this x value, instead of calling it x, if this thing was rotating around without the circle, we wouldn't know is this x, is this y, or whatever. But what it is the side that is adjacent, to the angle. So instead of calling it x, we're going to call it the side adjacent to the angle. And similarly, instead of calling this one y, we are going to call this one the side opposite the angle, Now we can take the circle out and our trigonometry equations will always work. So how is that going to work? Well, we're just going to rewrite these. X now is what? The adjacent side, the length of the adjacent side is going to equal r, which now becomes what? The hypotenuse times the cosine of the angle, like that. Okay, and you guys need to write this down because we're going to have one sheet of paper that has all the trigonometry that you're going to need for just about any problem. So we're rewriting these things when we have right triangles that are not superimposed on top of a circle. And similarly for y is not the adjacent, it is the length of the opposite side. The side opposite the angle is equal to the hypotenuse times the what? Times the sine of theta. Now this is exactly the same math, but we're just labeling it in a more useful and generic form. Now these two are still true. You still calculate radians from degrees the same way, and you still calculate degrees from radians the same way. Now we just need to rewrite these, that if I have the x and the radius, I would write it like this. Theta is equal to the arc cosine of what? X is the length of the adjacent side over the hypotenuse, like that. Okay, and here similarly we could get it with the angle theta is the arc sine of what? Y is the opposite over the hypotenuse, like that. Okay, and similarly we could get that same angle with the arc tangent of the opposite over the adjacent, like that. Okay, three different ways of calculating angle. All three of those are going to give you the same answer. And then we just up here, we just rewrote this in a way that we don't have to have a circle. So we see, this side is the radius, this side is the x, this side is the y. We just have the adjacent side is the hypotenuse times the cosine of the angle. The opposite side is the hypotenuse times the sine of the angle. And when we rewrite things that way, then we can more generically solve these triangle problems. And so let's come over here and let me kind of show you where we're just going to now go with this new nomenclature. We're just going to go with this new nomenclature, and let's just kind of go in and solve a few problems. So I'm going to turn this off, and now we're going to come in and we're going to look at this. And I've just sort of rewritten those, and now I'm showing it kind of, I've tried to just deliberately spin the triangle around where you can't think in terms of radius or unit circle or anything like that. But what do we have? We have a right angle here, and so the side opposite of the right angle is the what? It's the hypotenuse. This is the long side. The hypotenuse is what used to be the radius. Now for this angle theta, then I have the adjacent side and I have the opposite side. So the adjacent is the hypotenuse times the cosine theta. The opposite side is the hypotenuse times the sine theta. Or if I'm given adjacent in hypotenuse and opposite in hypotenuse, I can go in and I can calculate the angle. Okay, let's come in and just see if we can, solve a problem. Okay, let's say that I'm given that the hypotenuse is equal to 2, okay, and then let's say that I'm given that the angle is equal to 30 degrees. Okay, and so the hypotenuse I have is 2. So I'll label that there, and the angle is 30. Well, what is the opposite? Well, the opposite would be equal to, the opposite would be equal to the hypotenuse, which is 2, times the sine of 30, okay, times the sine of 30. All right, but remember I have to convert that to what? Radians, so I divide by 360 and then times inside the parentheses times 2 pi, okay? And so now what would the opposite be? So let's see if I can come in over here and call this up. And what do we need to do in order to do these trigonometric functions? We need to first of all get it where you can see what I'm looking at. I need to come in and I need to say import, and I'm going to import math, okay, and that went well. And so now what would the opposite be? It would be 2 times math.sine, and math.sine of 30 divided by 360 times 2 times math.pi, like that. And let's see what we get. Okay, 1. So when the hypotenuse is 2 and the angle is 1, then what do we get? We get the opposite side is 1. And that's sort of the magic of the 30, 60, 90 triangle is that short leg is half of what the hypotenuse is, which is what we just found. Well, how about the adjacent side? Well, the adjacent side, let's see here. Let me come back over here. Get rid of that. Okay. So now let's do the adjacent side. And so now the adjacent side is going to be equal to what? The hypotenuse times the cosine of the angle. All right. And so now we're trying to find this adjacent side. And so let's see what that comes out to be. Well, that is going to be the hypotenuse, which is 2 times math dot sine of what? Of 30. 2 times math sine of 30. And then I've got to convert it to radians, so I divide by 360 times 2 times math dot pi. Okay, and what is the length of that other leg? And I did something wrong there. Oh, I'm sorry. It is cosine. I wrote cosine on the tablet, but I didn't type it in, so it's cosine, as I just said right there. Okay, and that's 1.7. So this opposite side is 1. This adjacent side is 1.7 when the hypotenuse is 2. Okay, so I just solved that. Now let's kind of think about solving this a different way. Okay, and let's see if we get the same answer, just to sort of show you how you can think about this in an interesting way. Okay, so if this angle is 30 and this corner is 90, what does this angle have to be here? Well, the three angles in a triangle have to add up to 180. And so if one is 90, the other is 30, then what does this have to be? Let's label this one phi. That's got to be equal to what? 60. Now I've got a completely different problem. Now my opposite becomes my adjacent, right? Because my opposite here, now it is adjacent. So this time adjacent is going to be equal to the hypotenuse, which is 2, times the cosine of this angle, which is 60, okay? Which is 60. So let's see what happens when we do that. So this time it is going to be 2 times math dot cosine of 60 divided by 360 times 2 times math dot pi, like that. Okay. And look at that. Why did that not come out exactly? That should have come out exactly, but it's 0.999999. 1 to as much as you could do it. So you see this comes out equal to 1, and this one over here, this was the opposite. Okay. Do you see how this equation and this equation are different, but they both came out with the same number 1, that the sine of 30 times 2 is the same as the cosine of 60 times 2. So it doesn't matter if you solve the problem with this angle or you solve the problem with this angle, the length of the sides and the answers are going to come out to be the same. The length of the sides and the answers are going to come out to be the same. And so you can do it with the 30, you can do it with the 60. If you had a 21, you would have a 69. You see, it would just whatever adds up to 90, you can use either one of those, and then you can work your way around the triangle. So now I told you a place that we would want to use trigonometry. A place that we would want to use trigonometry would be when we were like trying to draw a circle or parts of a circle. Okay, where else would we want to be doing this? Well, we would be wanting to do this with problems involving vectors. Okay, and let me see if I can show you that. I'm just trying to back my way out of this. I think I can probably erase it here without to, yeah. Okay, so I just want to leave those equations on there. Okay, so like let me just show you an example of a vector type problem. A vector type problem would be like if you're flying an airplane north at 100 miles an hour and there was a 10-mile-an-hour eastwardly wind. What path would you actually fly along, right? It would make a triangle, that type of thing. Well, let me show you another one, just kind of to just think about different trigonometry problems that you run into that are practical. Okay, so let's go in and let's see if we can think about another real-world problem where you would want to use trigonometry. Okay, so let's say that I had a set of scales. Okay, so I'm going to come in here and I am going to draw my scales here like this. And now let's say that I stand on those scales. And when I stand on those scales, I weigh 180 pounds, and so I am going to exert a force downward onto those scales of 180 pounds. And what are they going to read? They are going to read 180 pounds because they read the force that is coming on them at an angle of 90 degrees, okay? But now let's imagine that instead of that, what I am going to do is I'm going to put those scales on an incline, and that incline is going to be an incline of what? Of 30 degrees. And so those scales now are going to be at an angle of 30 degrees from the gravitational force, and then let's see. Let me draw the scales here. And so here are the scales sitting on that incline, and that is at 30 degrees from the force of gravity. Okay, now what is going to happen? Did my weight change by standing on an incline? No, I still have the same amount of fat. I still weigh what? I still weigh 180 pounds. And so I can come here, and I am still having a gravitational vector of what? Of 180 pounds. So I'm still coming down 180. Now the question though is, are the scales going to read 180? No, they aren't, because they don't read the force coming down at an angle. They read the force that's coming in at 90 degrees. And so what would that force be? That would be this. This would be the normal force. This is the force that's coming in perpendicular to the scales. Okay, and so I've got 180 coming down, and then I've got something else coming into the side. And then what you can also see is there is another force here, and that is the force that is trying to scoot the scales down the incline. Will it scoot? Will it not? Well, it depends on what the coefficient of friction is. If the friction is strong enough, there's going to be a force, but it's not going to be moving. And if the friction isn't strong enough, it will start scooting. But we're not going to worry about that. It's just what we're going to see is we have got different things here. And let's see if we can kind of start labeling this thing now. Well, this angle 30 is going to be the same as this angle here because we've just tipped the triangle up. And so our angle is going to be 30 degrees. And now what is this? This 180 is the hypotenuse. It's the long side. The hypotenuse is 180 because the force that's coming in normal to the scales is going to be less than that. All right. And what is that going to be? That is going to be the adjacent side. Okay. And then the force that is trying to scoot the scales down the incline, that is going to be the opposite. Okay. So now what would the scales read? Well, the scales would read this adjacent component here. And so we can calculate that. We can say the adjacent is the hypotenuse. It would be this here. It would be the hypotenuse, which is the 180, and then times the cosine of the angle. And the cosine of the angle is 30. All right. And now what would be the force trying to scoot the scales down the incline? That would be 180 times sine of 30. Okay, and now let's just calculate those things. We would expect the scale to read kind of close to 180 because 30 isn't that much of a tilt. But then we would expect it to be a low number pushing it down because it's not very steep. So let's just do this and see what we get. So let's see, what do we predict the scales would read? Well, we predict they would read 180 times the cosine of 30, which now we have to convert, the cosine of 30, which now we have to convert. So we would say 30 divided by 360 times 2 times math.pi, like that. And when we do that, okay, maybe we need to, it's math.cosine, sorry. Math.cosine, like that. Okay, so what it's saying is these scales, instead of reading 180, they would read 155 because they're on a tilt, 155.9, let's say. And then how much force is trying to scoot those scales off of the incline? Well, that would be that same thing, only it would be sine. Okay, only it would be sine, like that. And that would be 90 pounds of force trying to push it down the incline, and the scale would read, for me, a 180-pound person, it would read weighed 156. So if you want to boost your weight loss program, just tip your scales a little bit. And if you tip your scales a little bit every day, you're gonna weigh less and less and less, as read by the scales. But of course, that doesn't really mean that you're losing weight. Okay, well, let's look at a different problem. Let's just say, what would it be? Like, what if instead of reading 180, what if the reading was, instead of reading, let's say at 30 degrees, it's reading 155. What if I am reading 175 on the scales? Then what angle am I at? Well, that angle is going to be equal to the arc cosine, okay, the arc cosine of what? The adjacent. That adjacent is the normal one coming in there, and that normal one is 175 over, what do I actually weigh? I actually weigh 180, and so what angle are my scales at? Okay, what angle are my scales at? And you couldn't see that, could you? Okay, so the angle is arc cosine of 175 over 180, and that should tell me what angle my scales are at. So let's try that. So what I'm going to say is, I'm going to say arc cosine. I'm going to say math.arc cosine of 175 divided by 180. And then that is going to give me the answer in radians, which is 0.236. So I need to convert that by dividing that by 2, divide that by math.pi, and then multiply that by 360, and that should say that I am at an angle of 13 degrees. So if my scales are at an angle of 13 degrees, I am going to read that I weigh 175 when I really weigh 180. Okay, guys, let's sit and let's think about this a little bit. Does this make sense, what we have done? This is really just the same stuff that we learned last week. Okay, but last week, what we did last week is we had the aid. Last week, we had the aid of this circle, and with the aid of the circle, we were able to very intuitively understand what those angles and what those numbers all meant. But then what we've got to do is we've got to see that we can't always be tethered down to that circle with nice X's and Y's, and so we had to rewrite things more generically, where we were doing things in terms of the adjacent side, the opposite side, and the hypotenuse, and then we could solve really any triangle. Okay, guys, I hope this made sense, and I hope you stuck with me through this. Because like I say, on this next lesson and next week, we're going to start getting into this 6-axis IMU with 3 accelerometers and 3 gyros. To get that thing to work, you've got to understand the trigonometry. And so I hope you have gone in. I really hope you've gone in. And if there's one piece of paper that you want to keep, is you want to keep all of this, because this is most of what you're going to need. This one sheet of paper, most of what you're going to need. Write this down, understand it, practice it, and then next week what we're going to do is we're going to jump in and start learning how to use that IMU. Sound good? Hope it does. Guys, I hope you're having as much fun taking these lessons as I am making them. As always, I want to give a shout out to you guys who are standing with me on Patreon. Right now, it's you Patreon guys that are keeping me in the game, keeping me making these videos week after week, because really I'm getting treated pretty poorly by YouTube. So it's you Patreon guys that are keeping me in the game. Other ways you can help me is give me a thumbs up, leave a comment down below. If you have not subscribed to the channel already, make sure you subscribe. When you do, ring that bell to make sure that you get notifications for future lessons. And then, as always, share this video with other people, because the world needs more people doing engineering and fewer people sitting around watching silly cat videos. Paul McWhirter with TopTechBoy.com. I will talk to you guys later.